Okay. For this particular session that we just had on multi-layer feed-forward neural network, the assignment is to implement this stuff, right? So this simple linear regression first, and then the multiple layer. Sorry, screen is not shared. Okay. Huh? No, the screen is not shared. I think we need to do something here, right? It's on the tablet. I will see this time so that next time will be able to. Okay, great. Okay, so as I was saying, for the lab session, one of the exercises will be to implement this single layer, like a simple linear regression type setup, and then try to do it for multiple layers. For multiple layers, you will have a problem. What is that? I haven't shown you how to do DL by DX yet, right? We have only done DL by DW. Where is that? So we have only done DL by DW. We will need DL by DX, because if you want to pass that backwards, you will need DL by DX. So that is going to follow very similar to this. So those of you who are able to do the simple linear regression, then we will see for them, we will try to do the multiple layers. Okay, so this is for this concludes, though there is potentially we could have discussed convolutional neural network as well, but this much if you can do, I think you get the basic gist of the things. You can try to figure out the convolutional neural network. And if you are able to do, for instance, all the exercises within that 1.5 hours, then if there is some time, then I can give you some idea on how to do that. Okay, so let's start the next topic, which is on clustering. So we will begin the next topic, which is on clustering. So clustering is unsupervised learning algorithm. Okay, so it's unsupervised. So supervised just means that you have both the features as well as the label. Okay, you have both the features as well as the label. But if you don't have the labels, you just want to group the data in some way, that is unsupervised. Okay, so let's look at an example. So let's look at an example of coins. Okay, so let's look at some coins. Let's look at coins that are there in India. So let's say rupees 1, 5 and 20. There are many other coins, but let's just focus on these three for the time being. Okay, so what is the problem? So problem is I want to create a vending machine which can detect which of the 3 coins you have put. Okay, so that's the problem. And so there will be 2 things I will measure. Okay, so one is x1 will be let's say diameter, and x2 will be weight. Okay, so I want to use a machine learning approach, which means I will just collect a bunch of coins. I will not try to see what is the exact label on the coin, but blindly make measurements. Okay, so you may argue that that is such a silly thing to do, because you know, why don't you give the labels as well, right? But many times problem will be much more complicated than this simple coins. It will be having many more things that you would like to capture. So measurements are typically easy, labeling is costly, right? Getting labeled data is always expensive, whereas you can get a lot of features, right? So you go to, let's say, Flipkart and you browse there. I will have all the information about you, but whether or not you will buy this particular pen, it is very hard to predict, right? So getting the features are easy. So in that same spirit, so let's assume that we have features for all these types of coins, rupees 1, 5 and 20. Let's say we have collected the two features, which is their diameter and the weight. Okay. And needless to say, like there is really physical difference between rupees 1, 5 and 20, right? So rupees 1, for instance, will have a small diameter and small weight. So when you make all these rupees 1 coins, perhaps they will group together in some region in this entire space, right? And then rupees 5, when you compare to rupees 1, it weighs heavier, but the diameter is roughly the same, right? So see, I mean, you can argue that when you take two coins, they will weigh exactly the same, they will have precise diameter, but that I say is a much more easier problem. Suppose if there is some kind of deviation and you plot it, it will have some spread. That's a more challenging problem. Okay, so if your problem is simpler than this, good, but perhaps it's not. So the problem is, like, the goal is not to explain this problem, but problems of this nature, right? So when you have general problem, there will be some noise, some variations, and yet you would like to identify what are those groups, right? So similarly, for 20, the diameter is considerably large, and if I'm not mistaken, the weight is between these 1 and 5. Okay, so the goal of clustering is that you have several samples like this. You have all the samples like this, which is just your labels, I from 1 to some n labels, and you would like to group them in some way. Okay, and ideally, I mean, pictorically, you can see that you would like to group them into these three areas. Like this is one group, this is second group, this is third group. Pictorically, everybody can understand that these are the three groups that I would like to get, right? And once you get those labels, what is the point? So one is you have reduced, you have summarized your data, right? So you had two dimensions, diameter and weight, and you have compressed into one single number, which is the cluster number. Correct? 1, 2 or 3 from two different dimensions, you have made it into just 3 points. So it's some kind of a dimensionality reduction, right? So if you are given lots of training data, you can always cluster it together and get single number for it. So that might help your learning algorithm downstream. Okay. So there are other techniques of dimensionality reduction, such as PCA, and other topics are there, LDA, linear discriminant analysis. All these things you can do to do dimensionality reduction. Okay. But do you understand the point? Like you can get like grouping points like this is an important task. So what do you want to do? So the goal is to get labels ZIs for every point, okay, in some particular way. So how do you tell which is good? So what is a good cluster? So we need to understand that, right? So what is a good cluster? So let's try, let me give you an example. So this is, let's say there is one cluster like this. And there is one more cluster for the same points. So which of the two clusters, A or B, would you prefer? Huh? B. You would prefer B because A is not, in some way it is not very good. Why is A not good? Sorry. But see, in 2 dimensions you can see this, but in higher dimensions you will not be able to even plot it. So you need to tell me a way which is general. Of course, when you plot it, you can tell. Yeah. So that is the thing, right? So basically what you would like is, like, you would like to minimize. So you would like to choose ZIs in such a way to minimize some L of Zi, which is the loss. Okay, so let me define what is the loss. L of Zi is basically Zij Just a second. So what is happening? I'm unable to rub. Okay, it went. Okay, so L of Z, Zi or okay, let's say L of Z is sum over I equal to 1 to n for all the data samples, j going from 1 to k for all the clusters. So Zij is going to be 1 if ith point is assigned to the jth cluster. Okay, so Zij is equal to 1 if ith data point is assigned to jth cluster. So Zij is that. Okay, now he said you want to minimize the total distance within a cluster, right? So that is just the distance between xi and mu j. Okay, where mu j mu j is what is called as cluster center. So what that means is like if I look at the cluster centers over here, roughly this could be the 3 cluster centers, right? Whereas the cluster centers are here for this example. So now if you look at the total distance within this cluster, it's kind of high because there is a lot of spread. Okay, in this cluster, so this compared to this, there is less. All the points are close to the cluster center. So do you understand why something is a good cluster and why something is a bad cluster? Okay, so this is what you would like to minimize, L of Z. The goal is to minimize this. Okay, and we will look at 2 different types of clustering algorithms. One is what is called as k-means, and the second one is what is called as Gaussian mixture models. Okay, 2 different things, and one which is very easy and one which is very hard. Okay, so let's see. So k-means. I'm presuming you might have already seen sometime, but let's just discuss it anyway. Okay. So the algorithm goes as follows. Okay, so initialization. So what you do is you randomly choose mu k, mu1 to mu k, okay, as cluster centers. So by the way, the input to a k-means algorithm is k. K is like how many clusters do you want? Okay, so there is now the question of how do you choose k? That we will answer at some point. Okay, so how do you choose what value of k to give for a unsupervised learning algorithm such as this? How do you choose k? We will try to answer that at some point, but assuming that k is given to you, we know that we are supposed to get k cluster centers. So what we do first is we will choose k arbitrarily k points as cluster centers with one criteria, that these k centers must come from your original data sample itself. Okay, so this is picked at random from your from your samples S. From your S, all the input data that is given to you x1 to xn, you choose some 3 of them as cluster centers. Okay, so in our example that we were seeing, perhaps I will get something like this. These are the two cluster centers. So the other non-cluster center points, let me show in other color. Okay, so this is the first step. Is that all? Is that all right? Okay, so then what next? So then you will have a loop. Okay, and the loop will continue so long as you don't arrive at some optimum. Okay, so what is an optimum? An optimum is a stage where you are not able to move into a higher value from that stage. It just remains at that point. Okay, so so that's the thing. So the first step that you will do is you will assign Zij. Okay, so Zij is going to be 1 if, so can you guess what I should do? So Zij for, let's say, t plus 1. So this mu k is the 0th iteration. Okay, so Zij is equal to 1 if when. So basically what I'm trying to do is I will look at, these are the 3 cluster centers that I have shown in the, if I can draw your attention to the figure. So you have these black points which are chosen as the cluster centers. So what I will do is I will look at every point and I will see which are all the closest points to that point, right? So perhaps I will get something like this. Okay. So the circles that I have drawn is basically all those points closest to the cluster center that has been initially chosen. There could be some errors because I might not have done it carefully, but you get the idea. Okay, is that all right? So Zij is 1 if xi minus xj, okay, this distance is less than xi minus xk. Okay, not xi minus xj, right? What it should be? Mu j, xi minus mu j. So this is how I will do all the assignments, all the points I will go through one after the other and I will do this. Okay. So this is the step 1. So this is step 1. Then step 2 is I will look at mu j of t plus 1. So t represents your how many times you are running the algorithm. So initially I started with mu 0, which is arbitrarily I have chosen a few points as the cluster centers. Okay, so next time when I go to the loop, it will become mu 1. Then again, when it loops again, it will become mu 2. Sorry. Yes. So here Zi, okay, this Zij is computed for, you will check it for all, you will do for all I and all the cluster centers. Okay, and mu I j of t plus 1 you will check for every j which goes from 1 to k. Is that okay? So you will compute all the cluster centers. What is the confusion? Okay. Okay, let's write the pseudocode. Okay, so I hope init is fine, right? Init I will choose mu 0. Mu 1, mu 2 up to mu k of 0. This is fine. Okay, so then I will have a for loop for actually I should be checking till it is converged, but what I will do is I will run it for long number of times. Okay, I less than or equal to 10 power 5. Okay, let me run it for a long enough time so that I don't have to bother about convergence. So this is the random loop. Okay, so now I need to check, okay, for input point which goes from 0, input point less than or equal to n, input plus plus. Okay, I'm going through every point. Okay, then I will loop through cluster index, which goes from 1, cluster index less than or equal to k, cluster plus plus. Let's say clusters, is going from 1 to k. Now I will look at, I will say z input, and I will compute the distance between input and cluster. Okay, this is equal to distance between x input and mu cluster. So this I will do. And then finally, I will have z input cluster, okay, is equal to 1 if it is the minimum. So that I will keep track of. Like, so how do I do this? So let's see. So distance, so let's say, so I can look at which distance is minimum. So minimum cluster is equal to min of d input. Is that okay? I look at all the distances from input to every other cluster and take the minimum. That is my minimum cluster. Okay, so then z input minimum cluster, this is going to be 1. Others are 0. So that is what is happening till here. Do you understand now? And what is mu j of t plus 1? I am trying to find the new cluster centers. So I will look at these blobs and I will pick points which are going to be new cluster centers. So let's just pick something which we can all see. Perhaps this will be the new cluster centers. Okay. Yeah. Yes. 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 So when the clusters don't change, then that means you are at the local optima. If the cluster assignments is not changing, so whenever, so from one loop to the next loop, zij's may change, right? So if that doesn't change by more than, let's say, 1%, then you stop. Okay, so what is mu j t plus 1? You look at all the zij of t times xi summation divided by summation zij of t. T plus 1, whatever came from the previous round. Okay. So cluster centers is also fine. So does everybody understand how this is going to work? Okay. See, already you can see once these new cluster centers that I have shown here, right, over these 3 points, they are coming closer and closer to what is really desired. So it's actually starting to converge. So in your lab exercise, you can do this today. So there is a data set which is called as what's that data set with the geyser, which that water comes, no, good old faithful, or good old faithful. So on the good old faithful, there is a data set, so you can try and implement k-means. If you have understood the algorithm, I don't think there is any problem. So that is going to be one of your second things to do during the lab. Okay, so okay, so this is k-means. Okay, so now sometimes there is a problem. Okay, so let me try to motivate what is the issue. So let's say your clusters actually came from points which looked like this. So visually you can see that there should be 3 clusters like this. One is this, another one is this, another one is this, right? Visually you can see that there has to be 3 clusters like this. But if you use k-means for a shape like this, there is going to be a problem. Okay, so k-means has some limitations. So there are limitations. The limitations being one is all the cluster sizes are same. Okay, sizes are assumed to be same. And secondly, they are having spherical contours. So they are like circles. You try to put circles of the same size and try to cluster. Okay, but in general that may not be the case. So you may want to fit ellipses instead of circles. Okay, so that is where we will use what is called as Gaussian mixture models. Okay, so that is the next clustering algorithm that we are going to study. Okay, so
sir,
yeah,
sir, for k-means cluster, for limitation, cluster size is same or it is dependent on initial condition, means number of clusters.
I couldn't make out. Can you tell slowly?
Limitation for k-means algorithm, size of cluster is same or it is dependent on initial condition, means number of clusters.
The sizes, the circles are of the same size. You assume that they are of the same size because from the cluster centers you are always taking whichever is the closest, right? So you are trying to see why is it the sizes are assumed to be same, because whichever is the nearest I am taking that as the cluster assignment, correct? So the sizes are assumed to be same, one, and they are all spherical, means every direction there is the same distance is like forms a circle.
The second point is clear, but first point means if for a specific cluster number of points is different for two. If we consider two clusters are there, and for a specific cluster number of points are say 5, and another cluster number of data points is 7. So size will be different.
I'm really sorry, I'm not able to understand. The voice is getting garbled. You have a question, perhaps you were telling? Yeah, you can send via chat. Before that, there is some question in the audience here. Yeah. Yeah. So that is the issue, right? If you are assuming that it's circle, so if you try to put the goal is given this. If I try to put 3 circles here, some points will get moved into the wrong cluster, right? So like if you take this as a circle, so this could be few of these points. So there is some kind of a error that is coming in when you assume they are of the same size, right? So that is the problem, correct? Yeah. Yeah, so that is another question that I didn't answer, but what you typically do is before we come to Gaussian mixture model, let me just say that. So you try to look at your loss. How good is the loss, average distance to the corresponding center, and versus K, the clusters. So what is the maximum K can I choose? Number of points. Every point can be a cluster center. So the loss there is 0. Okay, and minimum is 1. So that will be having high loss, right? You are just trying to put, so that will be here. So basically when you plot it, so you will have some kind of a elbow. Do you see? You'll have some kind of a elbow. The point where it is, it is elbowing out, that's the point where you stop. So that's the way you can choose a K. Okay. So did he type in the chat? Okay. So whoever was asking in the audience, online audience, you asked a question. Unfortunately, due to some reason, I'm not able to make out, your voice is getting echoing here. So you please type it in the chat and we will try to answer it at the end. Okay. So now coming, yeah. How is it? No, but see, how are you choosing the cluster assignments? You are looking at whichever is the minimum, right? So when you do that, each cluster center has it has a radius where there will be some over, like whichever is the nearest in that circle, that will be assigned to it, right? I'm not trying to, like, there is no, if it is cluster 1, I am not saying that the center is smaller. There is no trade-off. If you see what I'm saying, can be different in a Gaussian mixture model, which I am coming to, but in a k-means type of an algorithm, because I am choosing minimum, it ends up being the same size, right? Each cluster center, I am not treating it any different from any other cluster center. That means by symmetry, at least the sizes are same. Yeah. So let's just draw what is saying. So if there are a few points here and lots of points over here, yeah, the distance is very large. So then when you use k-means, yes, so it will work fine. But if the points are a little close by, then that effect will start manifesting. If they are well separated, always it will do well. But if it is close by, then there is a problem. That is one. And of course, k-means also has a problem of local optima, which means, that there will be two different assignments which can be possible. So anyway, that we will come back to later. But before that, yeah, I hope the point is clear. Yeah. No. Okay, first let me just say what is hard. So if you look at this computational problem of choosing the best possible across all possible assignments, if you want to choose the best possible, like the way you are describing, you want to try out every different arrangement, every possible way, that is known to be NP hard. Okay, but the way I described the algorithm, that is not a hard, no. So I am choosing something at random. That is not a very complicated operation, right? Yeah. You are talking about the elbow, this method, the point of choosing K. This you are saying is hard. Okay. Different laws. Yes. Yeah. So for different values of K, do you agree that there is a decreasing trend? Do you agree that the K, it decreases, the loss decreases, the average? Yeah. So what all I'm saying is the point where there is the losses diminish, in the sense there is not much benefit from going from K to K plus 1, right? So if you look at this, right, this is K minus 1 to K and K to K plus 1. The decrease in loss is quite high here, whereas the decrease in loss is not so high. Why? You look at the algorithm, right? So what is the complexity here? So NK, right? Roughly NK. You take the good old faithful data set and do it today. You can implement it. It will run in like 15 minutes or even less. Okay, it's not hard. What is hard is trying to, amongst all possible clusters, if you want to get the globally optimal one, that is known to be NP hard. Not this k-means. K-means is okay. All right, so let's come back to Gaussian mixture models. Any other questions on k-means? Okay. So, so how many of you are familiar with Gaussians? Can you raise your hands if you are familiar with Gaussians? Okay, so only few. All right. So, so it's like this, right? So, if you look at a particular population, let's say you look at only one population, let's say in India, if you look at for males, if you look at their heights, right, and you measure it. So typically what is observed in nature is that you have what is called as a bell shape. Okay, so you will have something like this. It's kind of universal. People have noticed that many things in life has this kind of a shape. Okay, for let's say this is heights of males in let's say Gandhinagar.
There is a question from online audience that
Yeah.
how do we evaluate the cluster obtained?
Yeah, so cluster obtained. Okay, there is a question on how is a cluster good. So that is computed via the loss. So if you look at this loss, this is telling how good a cluster is. So if this loss is minimum, that is a better cluster. So if you can get a lower value here, that's better. Okay. Okay. So is there any follow-up? Okay. So if you look at heights of all males in Gandhinagar, it seems to have a normal pattern. This is true for many things, right? So if you look at, I don't know, like lifespan of ants or, rainfall in a particular area during a season, all this seems to have this kind of a Gaussian shape. Okay. And Gaussians are, okay, there are multiple. So let's look at single variable Gaussians. So we have a density for this, which is fx of x, which is 1 over. I will explain this a little bit in detail, but e power minus half x minus mu whole squared by sigma squared. Okay, so something like this we have. So if you notice, right, so this function for x equal to mu, right, for x equal to mu, the value f of fx of x is maximum. Okay, so for x equal to mu, so this is the mu, the value is maximum, and then as you go away from this mean, the value is symmetric because x minus mu squared. So either if you go to this side or that side, negative or positive, it's the same value. So it uniformly decreases. Okay, so this is how the Gaussian shape comes, the bell curve comes. Is that all right? So this is how single variable Gaussians can be thought of. Now, just like this, you can also define multivariate Gaussians. Which is, instead of having just single parameter, you will have x1, x2, and so on. The value is 1 over 2 pi to the power d by 2. Let me explain this. Determinant of sigma to the power of half e power half x minus mu transpose sigma inverse x minus mu. Okay, so I will explain this in detail, but now what are we trying to do? So single variable Gaussians, I hope everyone understands. You look at IQ of people in certain places, it will have normal distribution, which means there is a mean. beyond the mean, there is a uniform either side symmetric decrease and it's reducing, right? But suppose if I look at two parameters, okay, so height and weight of people in certain population. So that also has to have the bell shape that is extended beyond just one dimension into two dimension, right? So height and weight, are they independent? What do you think? If someone is tall, what can you say anything about their weight? Yeah, there is some dependence, right? So that dependence is captured by this matrix sigma inverse. So sigma is a matrix which is called as sigma is a covariance matrix. Okay, so I don't worry about it now if you don't follow, but it's just a matrix. Okay, so sigma inverse is also a matrix. So x minus mu, so x is a vector. So x is a vector which is x1, x2, which has height and weight, for example. Okay, mu is the vector which is what is the average height and average weight, right? So this is like the center of the mass where it is maximum. So mu1, mu2. Okay, so x minus mu is what? It is a 2 cross 1 vector. Okay, so sigma is a 2 cross 2 matrix. X minus mu is a 2 cross 1 vector. So x minus mu transpose so if I take a transpose of a 2 cross 1, what will I get? I'll get 1 cross 2, right? So this is 1 cross 2. Sigma inverse is 2 cross 2. Then I'm multiplying with x minus mu, which is 1 cross 2. Okay, so when I multiply this, what is the final value? Yeah. What is it? See, it's just matrix multiplication. 1 cross 2 times 2 cross 2 times 1 cross 2. What is the final? It is 2 cross 1. Sorry. This is, I'm sorry about this. This is 2 cross 1. So what is it going to be? 1 cross 1. Yeah. So it's a single number. So this is a single number. So it's a single number. Okay. So do you understand how this is behaving? So there is some center, and as you move away from mu, that number becomes positive, larger and larger, larger and larger. Negative of that will become smaller. Okay, so if you imagine this for different values of mu, you will get shapes like this. So let me try to draw in 2 dimension. So this will be like a hill. This is the top of the hill. Then next level, next level. So something like this you will get. Do you understand? So it's like a cap. Okay, it's like a cap. The top of that is that smallest one, and like that. The center is mu1, mu2, the mean. Okay, so do you understand this? So one of the exercises today. So there are 3 things that you are going to do. First one is back propagation stuff that I discussed in the first class. Second is k-means, and since he said it's not tractable, elbow method. Okay. The third one is trying to draw points from this multivariate Gaussian and trying to plot it. Okay. So plot points from multivariate Gaussians. And show how it looks, what shapes you will get. So you will get circle, you will get flat, whatever shape you want, you can get for different values of sigma. Okay, so these 2 things you can try. So you will see that there are some problems when you try to do this 3, because we will see when you do it, you will have some issues. We will then address it then. Okay, so yeah, so this is about multivariate Gaussians. So are there any questions? So you understood like what was in a simple bell curve in 1 dimension has become like a bowl, inverted bowl in 2 dimension. Okay, and sigma changes the shape of the bowl, and that's basically the gist of what we have been discussing so far. Okay, is that clear? Yeah. Determinant of sigma. Yeah, it's a matrix, right? So it's, you can take its determinant, and so what you have asked is determinant, and to the power of half is square root. So determinant can be negative, right? So here the sigma, choice of sigma is made in such a way that it's always positive. Determinant of sigma will always be positive. Okay, this is something called as positive semi-definite. It's not important for now to know. Okay, but let's just assume that everything else is specified correctly. Okay. Okay. So did you understand this computation that it gives us 1 cross 1? So what is the minimum value you will get here? For x equal to mu, you will get a 0, correct? And as you take any other number, okay, because of the property of that sigma, the value is going to be a strictly positive number. Okay, so that is something that again I have swept under the rug, but you can, for any other value other than x equal to mu, the value will be a positive number. Okay, so negative of a positive number and e power that is lesser, so you will have that bowl shape. Got it? Okay. Sorry. So 2 pi, so 2 pi d is the dimensionality of your x. So x1, x2, d is equal to 1, d is equal to 2. Okay. All right. So some things I had not explained properly. Okay. So is that all right? So matrices which are having the property that x transpose ax is always greater than or equal to 0 are called as positive semi-definite. Sigma is a positive semi-definite matrix. So this number is always going to be, this over here, this number is always going to be greater than or equal to 0. All right. So so we have all this now. Now what is the whole idea? So whole idea is your points are not coming from simple circular shapes, but it is coming from these kind of weird shapes, right? So an example is if you look at perhaps, okay, this may be something that I'm just saying out of the top of my head, but if you, let's say, look at all population in this country and look at whether they are from low income, middle income, high income, okay, and then look at heights of children based on the income also added, what you may get, I'm again speculating here, but you may perhaps get like low income will have tend to, because of their nutrition, will not have as much height as the middle income perhaps, and then something like this you may get, right? Do you see what I'm saying? So you may be able to get shapes like this. Heights, I've just given an example of heights, but you may get shapes like this. Okay, so given all the heights, perhaps you can then look at the clusters and then you can tell, okay, this must be from low income, middle income, high income. You may be able to decipher that. We don't know, perhaps, right? So this is an example of Gaussian mixture model, because there is pi 1, which is proportion from the low income, pi 2, which is proportion of the people from high income, and pi 3, which is proportion of people from high income. Okay, and you have normal distribution, mean mu1 sigma 1 for the first, plus normal with mean mu2 sigma 2 for the second. This is again normal mu3 sigma 3. Okay, by the way, I didn't explain what is this sigma. Okay, so sigma represents how much, that's the sigma is the standard deviation. That represents how much is the spread. If sigma is small, the spread is not so much. If sigma is large, it spreads more. Okay, so Do you understand how the Gaussian mixture is coming? So my
Yeah.
population can be thought of, the heights of my population can be thought of coming from this mixture. Okay, is that all right?
Yeah, yes, sir.
Yeah. So now, so given this, so now the idea is, if you are given points like this, so if I give, so now because I am having in 2 dimension, if you visualize this, so you can now potentially look at problems which have shapes like this. You can have complicated shapes like this, because I can have different means and different spreads, right? These kind of shapes are possible. Yeah. Sorry. Yeah, that is the center. The in the Gaussian, whichever point takes the maximum, that's the center. The variation of that particular Gaussian is the variation. So that, sorry. Yeah, if sigma is larger, the cluster will become larger. Correct. So the goal is, yeah. So if someone told you what is if I gave you people exclusively from one income group, you can estimate mean and sigma. How do you do it? If I give you like points, how do you estimate the parameters? Sorry. No, I'm telling you that I have given you, let's say I give you low income people and their heights and weights, or let's say heights only I'm looking at. I give you all the heights. How do you estimate the mean and the variance for that? Huh? Average is the mean, variation, variance. How? Yeah, but what is the procedure? I mean, yeah, that's true. All of you, whatever you are saying is correct, but I'm just asking the technical name for this procedure. Maximum likelihood estimation. Didn't you do it yesterday? Yeah, so that's maximum likelihood estimation, right? So MLE. So given that I am from one group, I can estimate mean and variance like that. Okay, and but the problem is I don't know which group I am coming from. Okay, so that is the issue. I don't know that these people are coming from this group, these people are coming from this group. This, I just don't know that. I just have heights. I don't know which group they come from. Can you see the connection between the clustering example and this? So what is the analogous thing to cluster here in this example? What is a cluster? Yeah, whether it is low income, middle income, high income, that are the clusters, 3 clusters. The shape is defined by the sigmas that we have. Okay. Huh? So means if they are close, then whichever is the closest, you will have assigned it to that, right? Yeah, so then arbitrarily you'll break time. You have to give cluster centers to everybody in k-means. Okay. Sorry? Gaussian, yeah, Gaussian mixture model will come to when we come to that. Okay, so so let's try to, so the yeah, I hope the motivation is clear why you should consider sometimes the data as coming from mixture of Gaussians, right? The motivation should be fine to all of you. So let us try to see how do we go about actually doing something similar to k-means for this kind of a setup. Okay, so we will look at perhaps it's going to take a little more than this session. So some amount of the next session we'll spend on this topic itself. And because, yeah, so let's see. Okay, so we have about half an hour. Let's see. So So we will have to look at it in two different ways. Okay, so Gaussian mixture models is what we are looking at. So we will have to look at it in two different ways. So first is full information case. Okay, so what is the full information case? Is that your sample data points has xi, and also I am seeing which cluster it belongs to. Okay, and my goal is to learn mu1 sigma 1, mu2 sigma 2, mu3 sigma 3. Let's assume that there are only 3 clusters. Okay, so I'm telling you what is the mean. This is the kind of question that I was asking. How do you actually estimate using maximum likelihood estimator? But let's just do it because that's necessary for understanding. So suppose if I tell you, I will give you the height, and also I will tell you which income group that person is coming from. Can I estimate the mean and the variance? And the answer is whatever many of you told, take the average and everything. But I want to do it one step more and actually show you how mathematically you will do it, because that this particular technique is very useful. Okay, so let's try to do what is called as maximum likelihood estimators. Okay, so and of course this is this, and pi 1, this is pi 1, pi 2, pi 3. This is representing the probability that a particular point is in one cluster. Like this is the proportion of cluster 1, proportion in cluster 2, and proportion in cluster 3. So do you all understand what is pi i's and what is mu i's and sigma i's? Is all these parameters clear to you? Yeah. So so I want to estimate pi 1, pi 2, pi 3, right? So so what is the thing I want to find out? So by the way, so let's look at one particular example. So suppose I have a point x1. Suppose point x1, there is some value. Let's say point 1. Okay, is taking a value. Let's say some small x1. This is the value of that point. I take an individual. His height I am noting. Okay, that is x1. And suppose that person comes from population cluster 1. Okay, cluster 1. So what is the probability of this happening? Probability. So probability that that person lies in low income group is P1, pi 1. Okay, and you multiply it with the normal distribution, right? How so if that person is close to, so you have this, right? So see, if the person that I picked ends up being very close to the center versus this point, which is more likely? Is the blue point more likely or the other one? The blue point, because the cluster 1 is right here. So this is more likely versus that, right? Yeah. So this will be pi 1 times 1 over square root 2 pi sigma 1 e power x minus mu1 square by 2 sigma squared negative. So something like this. This is the probability. Okay. So now like this, I will look at every point and I will see which cluster it belongs to, and I will write this corresponding term. So for example, this was for point 1. Suppose for probability for point 2, this could be cluster 3, and then this expression will be sigma 3 e power minus x3 minus, so this is x1, x3 minus mu3 squared divided by 2 sigma 3 squared. Like this, I will do for every point like this. Okay. Now the goal, okay, so what should be the goal? I should choose my parameters pi. Okay, so I should choose my parameters pi, mu and sigma in such a way so as to maximize the entire probability of seeing that data. Okay, so that is that's what you are doing in your maximum likelihood estimator, right? So you remember the coin toss example? I think I saw that yesterday, right? So as you vary P, there will be a point where it is the highest, right? So that is the most likely estimate for these parameters. In the same way, I would like to find out the most likely estimates for pi 1, pi 2, pi 3 in this way. Okay, so that is the likelihood of seeing the data, and I would like to maximize it. So likelihood of theta. So this is the probability of seeing that. Okay, so I going from 1 to n, this is for the data samples. J going from 1 to k, this is like which population group am I belonging to. Okay, here I will look at pi j 1 over square root 2 pi sigma j e power minus x mu j squared by 2 sigma j. Okay, this entire thing. Okay, is it correct if I just multiply all the j's? By the way, this pi means you are multiplying. Okay, is it correct if I just multiply like this? I should multiply this one only if that assignment is in that cluster, right? Do you see what I'm saying? I cannot just multiply like that. I should multiply only if the ith point belongs to the jth cluster. So there should be zij to the power of zij. Zij is equal to 1 if ith point belongs to jth cluster. Okay, do I have this information, zij's? Do I have it or not? In general, no, but we are looking at full information case where we actually know all the z's. Okay, so now to solve this, we have to use what we need to do is we need to find R max, right? What values maximize this likelihood? Okay, subject to the constraint that summation pi j should be equal to 1. That extra constraint is there. I cannot take any pi j's I like. They should satisfy this. Okay, so this is what is called as constraint optimization. I don't know whether you saw this yesterday, but this one you have to use little bit more complicated method, but I will not go into the detail. I'll just tell you what is the final outcome. Okay, so final outcome is pi j's. So this will be as somebody told. This is going to be summation zij by n. Yes, it makes sense, right? You look at all the points that are assigned to the jth cluster divided by the total number of points, that is the pi j. Similarly, mu j will be equal to zij x minus mu j. Okay, divided by summation zij. So this is like you look at all the points that are in the jth cluster. Okay, look at all the points in the jth cluster. There is no mu j, I'm sorry. It's just xi. You look at all the points that are in the jth cluster, you take its average. One of you were telling, like, you look at whatever points in that income group and look at the mean. So that is what that is. Okay, and sigma j is going to be zij times x minus xi minus mu j squared. Yeah. Yeah, okay. So if I have a coin, yesterday you saw examples with coin, right? So let's say the coin has a probability of giving head as 0.2, right? I do it, let's say 3 times, head is 0.2, and if I get 3 heads, what is the probability of that? No, the probability of getting a head is 0.2. So I do it thrice. So it is 0.2 into 0.2 into 0.2 independent. That's why I can multiply. Okay. So in the same way, what I am saying is like you are getting xi, zi, like height and the cluster you are getting. Okay. So you look at probability of first point, multiply it with the probability of second point, and that is the likelihood for a particular theta that you have chosen. So what I'm saying is like, suppose your theta, by the way, theta consists of pi 1 to pi j. It's a shorthand for pi 1 to pi k, and mu 1 to mu k, sigma 1 square to sigma k squared. So this is a shorthand and writing it as theta. Okay, so it's so basically for a particular theta, which means an assignment of pi 1 to pi k and everything, you are looking at the probability of seeing the data. That is your likelihood. That is L of theta. Is that okay? Do you see why that is a probability? I am multiplying this, right? So this is, so pi j is the probability that the point comes from the jth cluster times this. Correct? And this will be only true if zij is 1. Otherwise, that term will be 0. And something to the power of 0 is multiplying by 1. No. So the 0.2, this is okay. This is for point. This one is saying for 0.1, probability of 0.1, and assumption is 0.1 came from cluster 1, whereas 0.2 in your data is coming from cluster 3. So is that clear now? So you understand why this is constrained, right? I cannot take any pi j's. Pi j's should sum to 1. Okay. All right. So so this is the full information case. Okay. So this case, full information case, is you see both xi as well as z's. Everything is seen to you. Now the challenging part is when zi's are not observed, right? So challenge is when zi's are not seen. So what you see is your sample has just xi's. Okay. You don't know zi's. You don't know what assignments to take. So how do you tackle this problem? Okay, so this is where we will use what is called as EM. So here we will use what is called as EM, which is expectation maximization. Okay, so this is so we will take it slowly and try to convince you that how to do this. So yeah, so let's say we want to do this. So you will take the likelihood. Likelihood is going to be product of what is the probability of seeing xi point given theta, right? So you were asking, no, that so this is the likelihood. What is the probability of seeing the ith point given theta? Multiply it with seeing the I plus 1. All these points you multiply, you get the total probability, right? So this is your likelihood. Now the problem is this likelihood is hard to compute. Okay, so if I take let's say I take the log of this. So log of L of theta, this will become summation I going from 1 to n log of p xi theta. Okay, and p xi given theta has to be further broken down I should look at every point and actual ways that point could have come, right? So what I'm trying to say is, like, if you look at this example, right? So if I don't tell you the cluster assignment, and if I tell you that this is the point that I got, right? So this circled point is what I'm getting. So can you say for sure which cluster it is coming from? You can never say, right? Even though it is very likely that it came from one or two, because there is a non-zero probability that it can happen from 1 or 2, there is a small chance that it came from 3 as well. Okay, so it's not fully clear which cluster center it is coming from. So we have to look at all possible ways in which the clustering could have, which could have come from which underlying cluster, right? So this is P of xi and zi equal to C given theta. Okay, so this is the thing. So we would like to find, so this I will sometimes like we will say this is L of theta, log likelihood we will write like this. I want to choose, goal is to choose theta such that theta is equal to argmax of L of theta. I need to be able to do some kind of procedure to maximize this L of theta. I need to have some procedure to maximize this L of theta. Okay, so you can use yeah, so you can use something like gradient descent here, but we will try to analytically do it. Okay, so we will try to take the gradient with respect to each step and try to give you some expression in terms of the gradient. So let me remind you, so P of xi, zi equal to C given theta. This is equal to pi c times 1 over square root 2 pi sigma c e power minus half sigma c squared x minus mu c whole squared, right? So this is what it is. So when you try to maximize this, so we have to take the derivative of this L of theta. So we have to take, okay, so first of all, some background about optimization, right? So if you want to, let's say I want to find argmax of a function. So why is it that we take the derivative here? Do you understand this? Why you are taking the derivative to find the maximum of a function? So because the idea is like, if the function is something like this, right? If you look at the maxima, the derivative there is 0. So you take the derivative and suppose this is the maxima point x star, f dash of x star is actually 0, right? So that's the whole goal of taking the derivative at that point and setting it to 0, hoping that that will actually be the maxima, right? But unfortunately, sometimes what can happen is that you can have even like something like this. Okay, so if you look at the first point x star, so let's say there is one point which is x1 star and another point which is x2 star. Both these points have f dash of x, it could be 0, right? So just taking the first derivative sometimes is not enough, but let's ignore this problem. The problem is when you take the derivative, set it to 0, you may get a minima as well. Okay, so we will overlook that. We will try to look at just the fact that taking f dash x equal to 0, and we will look at what value of x satisfies that equation, and hopefully that is the maxima. Okay, so the goal will be to take this likelihood and try to take the derivative with respect to that and see what it goes to. Okay, so I feel like there is some silence. Is there some questions? Is it too hard? People are following, right? Okay, I will believe you. So let's just do that very quickly. So L of theta is summation pi c f c given. Okay, so what I have done is that this expression I have written it as pi c times fc. Okay, everything else is same. So fc of xc mu c sigma c is nothing but 1 over square root 2 pi sigma c x minus e power, all that thing. I have written this as a shortcut. Okay, so now let's try to take the derivative with respect to different things. So let's try to take dl by d pi, say pi k, right? So again, now you see chain rule is coming. Okay, so when I try to take the derivative with respect to some k pi k, what will happen? So what is the derivative? So I going from 1 to n, what should I write the next one? What is the derivative of log x? 1 over x, right? So this is going to be 1 over summation pi c fc. I will write more and more short form. Okay, pi c fc times the derivative of the inner guy. So the only term that remains is what? Fc, right? So that we will write it as fk like pi k fk. Okay, so that remains. And so there is something that I have yeah. So by the way, so let me just come back to this. It's correct so far. We just need to add one more term. Yeah, that's correct. So this is right. So this is xi, that is correct. Yeah, and I told you, right? So we should have the condition that so this any theta won't do. I need to do argmax over theta L of theta such that summation pi k should be equal to 1, right? So this is what we need to do. So unfortunately, I was seeing if I can avoid this discussion, but there is one thing. So instead of directly, so the way to do this is, see, you know that to take the maxima, I need to take the derivative, set it to 0, right? But when there is a constraint like this, you need to do, instead of trying to maximize this, you will try to maximize something which is called as the Lagrangian. Okay, so again, there is no way around this, but just believe me that it is just this. Okay, log pi c fc as before, nothing new, minus lambda 1 minus summation pi k. Okay, so lambda is a parameter that we need to choose. So let's just believe that this is what you need to do. Okay, so what we have done is that constraint I have put it as part of my objective itself. Okay, yeah, so this is something that may be hard to digest. So if you are having any questions about this, you should ask me now. Yeah, so this is effectively it is 0, but it's not that so for a particular theta that may not be true, right? So when you are doing the steps, effectively it is 0, because summation pi k, when at the optimum that summation pi k is equal to 1, it cancels and drops off. But when you are doing the procedure, the pi k that you have chosen at the step may not be 0. Okay, so it's just that if you want to do constraint optimization, you need to add the constraint as part of your objective. That is one technique that is used. Okay, it's not too hard when you learn it, but at this point you do not have the necessary background is what I think. Maybe you do, but let's just keep this under the carpet for a moment. Okay. So now coming back to the gradient. So I would have done dl by d pi k, right? So when I do that, you will have the same thing, I going from 1 to n. So 1 over summation pi c fc, okay, and times fc. Okay, that we saw. It's the same thing as before. And then there is a extra term which is coming from here, which is plus lambda. Okay, this equal to 0 is one of the conditions. Why am I setting equal to 0? That same discussion that I had before, when in the top the derivative is 0. Okay, so this is 1. Then dl by d mu j. So for the jth point, if I want to take the derivative. Okay, so again, the step is very simple. It becomes I going from 1 to n. So what happens here? The first part is as it is, pi c fc. Now I have to now look at so let's see, mu j, right? So that means I am looking at the jth cluster. I should see what is the derivative for that. So that means I should do d by d mu j for 1 over square root 2 pi sigma j e power minus half sigma j squared x minus mu j squared, xi minus mu j squared, right? So this I need to do. This the part lambda times 1 minus summation mu, that summation pi k, that does not depend on mu j, so that doesn't come into picture. Okay, so what is this derivative? Can someone help me out? Again, chain rule, right? So it will be the same thing. So it will be so there is a pi j as well. I somehow missed that. Okay, pi j. Okay, so it will be pi j fj divided by summation pi c fc. Okay, so this because d by d mu j of e power something is the same thing first, and then the derivative of the inner term. So what is the derivative of the inner term? Minus half sigma j squared times 2 times xi minus mu j times minus 1. This equal to 0. Is that all right? Okay. So now the third one, dl by d sigma j squared. See, try to understand the idea, because this is simple algebra that I'm doing. So just try to understand what is the idea. Okay. So if you have any questions related to idea, you let me know, because I think whatever we are writing, we can share it with you at the end. So you can go through the notes. So that's not the problem. So then you can verify and everything. Okay. So now when I take a derivative with respect to sigma j, what happens? That's we have to see. So again, 1 over summation pi c fc. Okay. So now when I take d by d sigma j of that term, let me write it. Let me not write sigma j squared here, right? So okay, d by d of this guy. So what rule should I use here is the question. E power minus half Okay, so how do I take the derivative of this term with respect to sigma j? See again, where and all sigma j appears in this? There are two places it appears. Can you all see that? So there is a pi j by square root 2 pi sigma j, and then there is e power sigma j. So there are two terms. So what do you use for something like this? It's a product rule, right? So d by dx of fx into gx, you have to use product rule. Okay. So when I use the product rule, see again, you can go back and check the authenticity of these things. But so if I do that, what do I get? So first term, when I take its derivative, so it is minus 1 by square root 2 pi sigma j squared e power minus half to sigma j square x minus mu j squared. This is the first term. Then plus so pi j by square root 2 pi sigma j e power. So e power, the first, like that, the first thing will be as it is. Then I am taking the derivative of the inner guy. So what will that be? Minus 2 by sigma j cube. Minus 2 by sigma j cube times minus 1. Okay. So this entire term is equal to 0. So these are the three terms which we have got. Okay. So yeah, so this is what we need to do. We will take terms one by one and try to solve and get a expression for this. Okay, this is just how it is. I mean, it's a little complicated, but it's not too hard. So we'll start with the first term. So dl by d pi k, I will write it. I'll multiply this entire thing with pi k, right? So I did a mistake here. This is pi k. Okay. So I will write it as pi k f k. I have multiplied pi k with everything. Okay. So by summation pi c f c minus lambda equal to 0. Pi k lambda equal to 0. Okay. So therefore, so this is fk of xi given mu k sigma k. Just I'm writing this because it's necessary. So what I will do is we will introduce one shorthand. So let pi k fk divided by pi c fc summation, right? This be equal to gamma I k. So why did the I come in? Because I am summing over I, right? So for different values of I, there will be different terms. This pi k fk xi is there, no? So for that I am calling it as gamma ik. Okay, so we will, so this xi is there, that's why we are having that. So when you do that, what you will get is that summation I equal to 1 to n gamma ik minus pi k lambda is equal to 0. Therefore, pi k, I think it was plus lambda. So let's write it as plus lambda plus. So pi k is equal to negative summation I equal to 1 to n gamma ik by lambda. Okay. So this you can get. So this is true for this one, is true for all k. Okay. So what you can do is I'm going to skip the step because it's getting too algebraic. So you can show, okay, by if you sum the box, you sum the boxed equation, okay, across all case, and you will get that lambda is equal to minus n. Okay, so this I'm going to skip. So what I'm saying is you just sum So when you sum, what will you get? So there will be a summation over k, summation over I gamma ik. What is summation over k pi k? 1, right? So that way you can solve for lambda, and it turns out that lambda is equal to n. N is this, I have written as small n, but big N, but it's actually small n. So this is small n is the number of training samples. Okay, so basically what you will get is pi k is equal to summation gamma ik by n. Okay, so this is what you will get for the first. Now, this is the difficult part, but if you do the second and third, you will get this. I'm going to skip this again because it's again becoming too complicated. So pi j will be, actually, if you do this, you will get pi k summation pi k xi divided by ik. Okay, so this is I equal to 1 to n, I equal to 1 to n. So this is pi j, by the way, sorry. Okay, so and then sigma j squared, if you solve for this, will be so these are the three things that we will get if you solve, but there is a problem. So what is gamma ij? So let me just remind you what is gamma ij. Gamma ij is actually equal to pi j fj divided by summation pi c fc. Remember, this is what we had originally put this substitution, right? So what is the problem now? Pi depends on gamma ij, pi mu and sigma depends on gamma ij. Gamma ij depends upon pi mu and sigma. Do you see the problem? See, forget about the algebra that I did. You can go back and check if that is correct or not at a later point, right? Some small mistakes might also be there. But I'm saying, so what was the goal? So we were having an issue which is like this. Okay, so let me remind you what was the whole idea. So you had a where is this? Yeah. So you had a problem that, okay, yeah. So you had a problem that your training samples are too close by and circular fit is not going to work well, right? We cannot take circular fits. So what we need to do instead is need to have some kind of a mixture of Gaussians. So that's where we started from, correct? So then we said, suppose if then we went down and we assumed that suppose we knew these sigmas, like if you know xi and zi, we showed this. I want you to particularly pay attention to these three equations. In fact, just for those here in the classroom, I will just write it here, because when I scroll down into the so I will leave that as it is, but just for you to see, pi j is equal to zij by n mu j sigma j squared so this mu j hat is the same thing I'm using here, okay, by the way. Okay, so this is what we intuitively said that this is what we should do. If you know the samples, you just collect them together and get the average, right? That's what you said. So now, after we did all this complicated math and all these derivations and calculations, we got this. So can you see the similarity? Can someone tell me what is the similarity? What's the similarity between this and what we derived? Yeah, so whatever was zij has become gamma ij. Okay, and gamma ij, if you notice, what is the property of gamma ij? What if I sum over all possible j's, what do I get? If I sum over all possible values of j, what do I get? It is a probability. It sums to 1, right? If I sum over all possible values of j, it will be like pi1 f1 plus pi2 f2. All of this will be coming in the numerator. So that is the same as the denominator. It becomes 1. So it's like probability. So what was here like a deterministic assignment, what was perfectly known here has become probabilistic there. Do you see the connection? Okay, so this is what we will exploit to. So I have not yet told you how we can arrive at mu sigma and pi k. How do you optimize it? There is a problem. Do you see the problem? Problem is pi, mu and sigma depends on gamma ij. Gamma ij depends upon pi, mu and sigma, right? That's the problem. So there is a very simple fix for this problem, which is the EM algorithm, which we will discuss. Okay. So for now, even if you didn't understand the algebra till this point and this similarity, do you see? So that is one important thing. Second thing is what was deterministic, like what I knew perfectly here. Now I am just having a probability. Do you understand that gamma ij is a probability? Yes, because it sums to 1. If I take over all sums to over all j, it sums to 1. Okay, so after the lunch, I will just conclude. I'll briefly wrap up this, and then we will look at decision tree and random forest briefly. Okay, yeah. Huh? Yeah. So there is one question. We will just take a few questions and then we will wrap up. Yeah. So how much more? Huh? Yeah. Yeah. Okay. Here. There should be. First equation I am taking with respect to pi k, right? So the log term will become 1 over summation, and pi k fk, that only remains fk comes pi k d pi k by pi k is 1, and then coming inside there is minus lambda times minus pi k, right? That becomes minus 1, so that becomes plus lambda. Is that okay? It's okay, right? All right. So yeah, we will continue after lunch, just briefly and finish this discussion before we start other things. So all right, so you can come back and come here and ask questions if you have. All right. Okay, so thank you.